Okay. So can anyone tell me in week 11 session how much have you done?
Not yet, ma'am.
But there was one session on Thursday, right? Last Thursday or Saturday.
Yes, ma'am. Nalini ma'am covered, ma'am. Week 11 till half, I think.
Yeah, that's what I know. Nalini covered week 11.
Yes,
So
ma'am.
which topics are left?
1 minute.
Is RAID architecture covered?
No, ma'am.
Okay. Backup strategies?
I don't remember, ma'am.
Ye- Yes, ma'am.
Okay.
Full and incremental, right?
Yeah, like incremental backup, full backup, that part. Differential.
I
So week
think
11, we also had those commands like read, write, transactions. Okay, so I think some topics are still left, right? Okay, week 12, have you gone through the lectures?
No, ma'am. That is very difficult, ma'am.
Yes. Okay, so just do one thing.
Uh,
You'll check that in week 12, last three lectures, right? Week 12, so 12.3, 4, and 5. So those are mostly theory. And there is no need to actually memorize those things. Okay, if you want you can go through that, but whatever we will discuss today is the main important topic for week 12, and question will also be from here on.
okay, thank you, ma'am. Because that in 12.1, that formula and all very did not understand, ma'am.
Yeah, yeah, yeah.
Thank you, ma'am.
Now
That
it
you are
is
covering today, no, ma'am.
yes, I'll
Thank
come.
you, ma'am.
Is my screen visible?
yes, ma'am.
Okay, one more thing I wanted to ask. Actually, I got a feedback from your last class that so the week 10 lecture that I took, was that okay for everyone? Like, is there anyone who attended that lecture?
Yes, ma'am. It was okay. It was
All
very
right.
good actually.
I got a feedback that I didn't cover numericals, but I do remember covering some numericals. So if you still have any doubt in that two-phase locking part, okay, you just let me know. I can cover more numericals if you want. Okay, so the first topic here is query processing. Okay, so what is query processing? Mainly three things are done here. Okay, parsing and translation. So first we receive a query, any SQL query or normal. Okay, like you select from where query. So what does a parser do? Any idea? A parser is basically going to check the syntax and semantics of that query. Okay, that whether it is correctly written or not. Semantics means that, say, if I write a query like this, it says select star from students. Okay, some students table is there. So the parser will like do the syntax and semantics analysis. It will also check whether this students table exists in the database. If you are, say, selecting some attribute to be displayed from that table, it will check whether that attribute or the tuples that you want to display, those actually exist or not. Okay, and a translator does what? A translator will convert the SQL query into equivalent relational algebra expression. Okay, but for a single SQL query, there can be more than one relational algebra expression as well, right? Just a second. Okay, so I'll give you this query. Let's say I want to find the salary of instructors whose salary is less than 75,000. Okay, so what is the SQL query for that?
Select salary from instructor where
Select
Salary less than
salary
25,000.
from instructor
from instructor
where salary is less than 75k.
right.
Less than 70.
So this is the SQL query. Now what can be the equivalent relational algebra expressions? See, one expression can be, I'm writing it here. I can make a selection operation outside, okay, of salary less than 75,000. And the inner operation is a projection of the salary attribute itself from instructor table. This can be one,
Yes,
right?
ma'am.
That is first I'm projecting, then I'm adding the filter of salary less than 75,000. Another expression can be what? I do the projection later for the entire attribute, and inner part I'll do selection of salary less than 75,000. This will also work, right? This will also work.
Yes, ma'am.
So which one of this is more optimized, do you think? Which will take less time or less cost?
Second one.
Second
First
one.
one.
Okay. So the answer is actually second one. Why? Because first we are applying the filter. Okay. So here only we are diminishing the number of tuples that we are actually having to project, right? But here you are projecting the entire attribute first and then adding the filter. So there will be a difference in cost. This one will be more efficient. Since the filter is added first, internal, then outer operation is projection. So like this, see, for one SQL query after the parsing and translation happens, there can be more than one relational algebra that is generated, right? Like this. So what will it do? It will then optimize it, like take the most optimized relational algebra expression. For that, it will use statistics, like data statistics, like number of tuples that are present in the relation, what are the keys of the relation, if any kind of indexing is there, okay. All of these things it will check. So optimizer does what? It chooses the relational algebra expression that has the lowest cost or that is most efficient. Okay. So that happens here and it gets the statistics about the data from outside. So optimizer does that. Then what happens? Then it makes the execution plan, like how this query will be executed. The relational algebra that you chose, that was chosen by the optimizer, now you have to execute that using the help of what? The evaluation engine, which will again take some data and it will actually evaluate your query. What is this data? That is actual data from your database, right? On which you are executing the query. Now, if you want to try this in Postgres and see what is the execution plan, what it looks like. So my Postgres is having some issue here, but I'll give you the command, okay? Let's say in the university database, okay, or any database basically. Let's say in FLIS. So if you write select name from players, or you can even perform some join if you want, okay, and then just put this whole in parentheses and in the beginning write explain, okay. Now run this entire line together and you will see that the entire execution plan will come as a result, okay, in the query result part. Try this yourself. That will show you the execution plan, like what is the sequence, in what sequence the query execution happens. So is the query processing basic steps clear?
Yes, ma'am.
And the parser generates many relational algebra expressions,
Yes.
right?
Yes. No, parser actually does the syntax and semantic analysis. Okay. The translator will give rise to the relational algebra expression.
Yes.
What
Yeah.
is that command you are saying? Exist, and inside that select name from
No,
place.
this is explain.
Oh,
Explain. Then inside you can write any query. Even if you can write some query using a join, then the sequence will be better. I mean, execution plan will be more easier for you to read. Okay. Let me try once if I can. It wasn't working for me. Actually. My Postgres is not working properly. Okay, you just try this command. You'll see the execution plan. It will come in the query result part. Okay, so this is the same thing that I just showed you. Optimization, how it happens. So for this SQL query, there are two different relational algebra expression, and which one is the more efficient? This one, right? Because filtering is happening first. Now, what do we mean by query cost? That we want the query which will have the least cost. So what are the measures for that, like metrics? Okay. So cost is generally measured as total elapsed time for answering query. That is the entire time that the query is taking to be executed until we get the result. Right. So many factors are there, like disk access, CPU, network communication, everything is there. So disk access, what do we mean by that? Why do we need to access the disk? Anyone?
Read, write.
Read and write data.
Right, because our database is actually stored in the disk only, right? So we are
Yes.
only, whenever we process, the part that we want to process, right? We just bring it from the hard drive to the buffer, main memory buffer, and then perform our operation, and then we store it back. Okay. So among all of these costs, the main thing that we will focus on is number of block transfers and number of seeks. So what do you mean by block transfer? Block transfer means I am transferring one block of data from hard disk to the main memory buffer. Okay. And seek, anyone remembers what is seek time?
The time taken. Go to the track.
Locating the disk, man.
Yeah, locating the track.
Locating the particular track where the data is present, right? That is seek time. So here, these are the only two factors that we are going to consider to calculate the query cost, just for simplicity. Okay, there are many other factors also. Okay. So for simplicity, we just use number of block transfers from the disk and number of seeks as the cost measures, where T subscript T is what? Time to transfer one block. And T subscript S is,
Just on interruption, that query you shared, right? It is giving this output sequential scan on player.
yeah, that is the execution plan. That
Okay.
sequential scan, you see there will be some text inside the brackets. What is it reading?
Yeah, I shared in the chat. It says cost 0.001 something.
Yeah,
and
so that cost that came, that was the execution time for the query. Okay.
Okay.
See, number of rows, all of these things are, that's why if you use like a natural join or an inner join expression, then there will be multiple steps, so it will look better, like how the relations are actually joined. Okay. So small ts is what? Time for one seek. That is, whenever you change the position of the read-write head, that is one seek time, right? So cost for B block transfers plus S seeks is what? B into TT and plus S into TS. Okay. So we ignore the entire cost of processing for simplicity. Only these are the two metrics that we will work with. Now, before I come to this, let's take a small numerical. Okay. I'm just writing in the side of this slide only. So let us consider that I am giving you some of the statistics for searching a condition within a given relation. Okay. So let's say the data given to me is number of blocks containing records of the relation. Let's call it B. There are say 200 blocks. Okay. What do I mean by this? Number of blocks containing records of the relation. That is how many blocks it is taking to store the entire relation in your hard disk. Okay.
One block can have more than one.
Yeah, definitely you can have. It depends on the size of the record. Okay. Second one is time to transfer one block. Let's call it TB. That is given as, let's say, 0.6 milliseconds. And the third information given to you is time for one seek. Let's call it TS. And seek time is, say, 8 milliseconds. Okay. So the question is, what will be the cost of selection query using linear search file scan? Now, before you answer this question, now I will take this chart first. Okay. See, in this chart, only these three are mainly important for exam. Okay, and that is the cost part only. This rest of them also you can go through once, just understand what it means. Okay, I will tell you what this first one means. See, so how much time is actually going to be spent performing a linear search? Everyone remembers what is linear search?
Yes, list, typical example.
Right. So linear search means I have to traverse one by one, right? I have to start from the beginning. And what is binary search? Anyone?
Dividing, it will be sorted and dividing and win.
Right. So I can take the middle element and then again check which part of the list I will check in, right? So every time in a binary search, every time we find the middle element, we are actually dividing the list in half, right? So which one is faster, linear or binary?
Binary,
Binary.
And what is the time complexity?
log n,
What is complexity for linear?
N.
O of n.
O and
No, N.
Order of n. Okay, very good. So linear search takes what time? It will take one initial seek, okay, plus BR number of block transfers. Block transfer means what? Transferring one block of data from hard disk to main memory. Okay, so if it takes one initial seek, so I just said that TS is representing seek time. So there is one seek time. And why one initial seek am I saying? Because once you place the read-write head at the beginning of at the point in the track where the first data item is stored. After that, everything is contiguous, right? So after that, you don't have to move the read-write head. You just have to rotate the disk. So that's why seek is only once, right? You only have to place the read-write head at the correct position once in the beginning, from where
So
you start the search.
that means the entire list, if, for example, that all the elements will be there in only one track.
Yes, only in one track.
Okay.
That's why only one initial seek. So once, like, this is our disk, right? Okay. This is the disk. So let's say in this track it is present. So you start searching, place the head here, and this is the point where you're starting the search. After that, you just rotate the disk like this. You don't have to move the head, no. And as long as you're not moving the read-write head, there is no seek. Okay, we just rotate the disk to get the contiguous memory locations. So one initial seek will take one seek time, and if it says BR block transfers, that means how many blocks how many blocks of data I'm transferring from the hard disk to the main memory. So if there are BR block transfers and one block transfer takes TR time or TT time, then what is the total time in that? BR into TT, right? So sum of both of this is the cost for linear search. Is this clear?
Ma'am, here we are not taking rotational latency, right?
No. Only seek time and this block transfer.
So that is a simplification.
Yeah. There are more, actually simplifications is a not correct word here. If we talk about simplification, we are actually eliminating the entire CPU cost. Okay. So whatever cost we are measuring, like the disk in the disk, from the disk to main memory transfer, seek, there we are only taking these two components. There are other components also. Okay. So is this expression clear? The first one?
Yes, ma'am.
Yes, ma'am.
Now it is saying linear search on key. That means since at most one record satisfies the condition. So this is actually the same thing, okay. But now what happens? This one is the worst case complexity, the first one. Next one is the average case. Okay. Average case means I only have to access half the blocks. Why? Because what is the average case? Let's say in linear search, let's say my list has 9 elements. If the middle element or fifth element is actually the key that I'm looking for, right? Then I only have to traverse half the list, correct? So whatever
Yes, ma'am.
was the number of block transfers is now going to be half of the original.
Yes.
So that's why BR by 2 into same block transfer time to transfer one block and one initial seek. So this is the average case of that same linear search. Okay. Similarly, this one is for tree actually.
Here, why we are dividing B with, dividing B.
Dividing B because this is actually the average case of that linear search thing. Okay. So if I have 9 elements in my list, in my average case, the fifth element will be the one where, let's say fifth element is the one that I'm looking for, is the key that I'm searching. So linear search means what? I have to traverse one by one every key in the list until I find the key that I'm looking for, right? So if the middle element is the desired key, then I only have to traverse half the list, correct? After half the list, I will find my middle element. So I don't have to traverse the rest of the list.
Okay.
So number of block transfers will be divided by half.
Yeah, but it can be the last element also.
Yeah, it can be, definitely. If it is the last element, then this is the worst case. That is the maximum number of block transfers.
Best case is the one element, when the first element, when the
Yeah,
worst
best
case
case
the
is
last
always
element.
first element in linear search. Then you just need to do one initial seek and one block transfer.
Yes, sir.
Okay. So the third one is actually on for B trees, B plus trees, this thing. See, it is actually about primary index. So index is implemented using the help of trees, right? Those are tree data structures. So index lookup traverses the height of the tree. Okay. This hi is nothing but height of tree. And actually this formula, see, index lookup traverses the height of the tree plus 1 IO to fetch the record. So each of these IO operations requires a seek and a block transfer. Sorry. So as many IO operations or input output operations will be there, that many seek and block transfers will be there. Okay. And how many of those IO operations will be there? Height of the tree plus 1. Okay. So can anyone tell me why it is height of the tree plus 1?
Because the height of the tree is one less than the level, or we have to compute all the levels, so plus 1.
In this case, it is the primary key, so it will be in the B tree, the B plus tree, right?
Right. So why that many number of TT plus TS? That's what I'm asking. Because every time we reach a particular height, right? Every time we are searching in a particular level of the tree. So at that time, I will transfer one block from hard disk to main memory. So every time the read-write head position also has to be changed because the heights are different levels, right? They are not contiguous locations. So every time I do that, every time for a particular level of height, I need a block transfer as well as a seek time.
Ma'am, that first you will seek. Once you identify the block, then only we will transfer. No, ma'am. That is.
Yeah, that is why TS plus TT. So first you have to do a seek in the particular level of height and then a block transfer. Okay. So whatever is the height, if the height of the tree is 3, if age is 3. Okay. So you have 4 levels, 0, 1, 2, 3. So it will be 3 plus 1 into whatever is 1 block transfer time and whatever is 1 seek time. Addition of those. So this first.
No, ma'am. If the height is 3, so 3 plus 1, 4 into the seek time, right? Then if I do that seek, I'll go to the block.
See, but for every particular, like every time you do that, every time you're seeking on a different level.
Yeah.
Okay. So that time one seek will happen and one block transfer will happen. Okay.
Oh,
like
okay.
in the first level, let's say in this tree, in the first level, here when I reach this, I will do one block transfer to transfer the data from this level.
Okay.
But before I do the block transfer, I have to position the read-write head at the correct track.
That is the seek. Yeah, that I understand, ma'am. You have to seek. My question was, okay, the condition checking also, for that also I have to bring the block. Okay.
Yeah. I have to bring
Yeah, that's clear.
So that's why TT plus TS and age plus 1. Okay. So these first 3 formula you can remember, and rest of it you just like go through it and try to understand what it means. Okay, no need. I won't say don't memorize all of them, but first 3 is important.
Ma'am, why we are adding 1 to I? Explain that part.
Okay. So you tell me, if I write, if this is my tree, okay, what is the height of this tree?
2.
Level 0, level 1, level 2. Right? But how many actual levels are there? 3.
Yes, ma'am.
So that's why height plus 1. Okay. Whatever is the height plus.
Actually, in the PDSA course, if the one element is there in the root node, then the height is counted as 1. But in the DBMS, why we are counting like this if the root is 0?
No, this is actually this is.
No, height is always the the maximum number of edges.
Yeah. I think you are talking about depth of the tree, right?
Not
Height
sure.
and
Maybe
depth
I
are
got
different
confused.
things.
Okay.
But whenever height we talk about, height starts from level 0 only. No? So if the height is 2, then actually there are 3 levels. So you have to go from level 0, level 1, level 2. And each of these levels, every time we check on a particular level, what we do, we take a block of data. I mean, wherever this data is stored on my hard disk, I will take that block of data. Now to reach that block of data, I need to do a seek to find in which particular track sector that data is present in the disk. So for that, you need a seek time first and a block transfer to the main memory. Okay.
We are
But
doing a block transfer to check all the values in the block and see where our
in
value lies.
whatever scan you want to do, whatever operation you're performing on the tree, okay, on the index. So whenever we are trying to look for a particular key in an index, then you have to do it block by block, right? Every block you have to check.
Like whether we have to go to the left tree or right
Yeah,
subtree.
exactly. So after you take it to the main memory, then you can find that or perform whatever operation you need. No operation can be performed in the disk itself, right? You need to bring it to the main memory buffer first. Can now answer this question. Can you answer this? So number of blocks containing records of the relation is what? 200. So 200 blocks of data are present for this relation in the disk. Okay. Time to transfer one block is 0.6 milliseconds. Time for one seek is 8 milliseconds. So if I want to run a linear search for a selection query, then what will be the cost? What is the answer?
One
Look at
seek
this.
plus BR into T.
So it is, what is the formula? TS plus BR into TT. This is the formula.
Yes, ma'am.
What is TS? 8 millisecond. What is BR? How many
It
blocks?
was 6 milliseconds, no? It was 6 milliseconds. Yes.
No,
0.6.
TS is this one. No?
Okay.
Okay. See, so 200 blocks are there. So how many block transfers? 200 block transfers into what is one block transfer time? 0.6. So this gives what? 128 millisecond. Okay, this is the cost. So this type of question might come. It's very straightforward, just have to put the values in the formula. But just remember the first three, that is enough. Okay.
This 128 milliseconds, the time taken for us to find out how many times a particular value is in the list, like searching.
This is the cost for this selection query using linear search file scan.
Yes.
Okay. That is selection part of the query. Okay.
Also in this tree,
Hmm.
like all the nodes, they don't lie in a track, in one track, is it? Like because we are seeking each time.
No, they don't lie in one track. That's why
Okay.
every time we are going to a different height level, we are seeking again.
Okay, each level will be in different track.
Yes. Because tree is not stored contiguously. Okay. Okay, see. Now those topics are over. Now we are going to check.
Ma'am, just one doubt in the previous one. I'm actually not able to correlate that measure of query cost and then this algorithm cost what you shared. So there it is B into T plus S into TS, but here it is different, that linear search.
Yeah, see. This one is basically a generalization. Okay. That what factors we are considering to calculate. Now, whatever algorithm I want to calculate for, like that linear search or whatever I want to calculate that for, everything will be based on these two metrics only, this TT and TS. So there can be different forms of, like different formulas, but based on these variables only. Okay. Like this BR is what? If you want to correlate, this BR is what? Number of block transfers. So B block transfers. This B is actually BR. Okay. And since here I'm doing only one seek, so 1.ts, this s is just 1. See, rest of the formula is same only.
Okay, but basically the first one is the generalization, like these are the parameters we have to keep in mind. But when the question asked, we have to look for this algorithm cost.
Like whatever, according to the question, you have to formulate it.
Got it.
Like here I know that only one seek is required, so 1.ts. This s is 1. Okay.
Yeah.
I'm also remembering only understanding these first 3 rows are enough for, at least for the exam, right?
Yes. See, for exam, only remembering this first 3 formula is enough. But just for your better understanding, you can go through the rest of the table also. No need to memorize. Just the first 3 formula. See, now there are different types of joins. So till now you have learned about inner join, natural join, right? Left outer, right outer, all those joins. So what is a theta join? Anyone knows? See, when I say I want to join relation M with relation N using some theta join, this theta is nothing but the condition. Okay. So basically any join, but we can specify a condition. So in an inner join, what is natural join? It is a special case of inner join only, right?
Natural join is performed when the attribute name is same.
Natural join is when we join two tables based on all the common attributes together, right? But in inner join, I can specify based on which attribute I want to perform the join.
Yes.
So these conditions, these are what the theta indicates. Okay. So any join can be written like this in this format. So there are several different algorithms to implement such joins, like to implement an inner join, to implement a natural join. There are different algorithms. So these are the 5 algorithms, but out of this, in our syllabus, we only have the first 2.
Ma'am, can you explain theta join again?
See, it is nothing. This, if I say I want to join relation M with relation N, if I want to do a natural join, then what is this theta? Theta is basically just stands for the condition.
Okay, kinds of join.
Yeah, let's say M has A, B, C, these 3 attributes, and N has B, C, D, these 3 attributes. So if I want to perform natural join, what is my theta? It is I will join wherever B equals to B and C equals to C, right? That is M dot B equals to N dot B and M dot C equals to N dot C. In natural join, I have to join all the common attributes, right? So the theta is just representing that.
Yes, ma'am, got it.
Okay. Now these are the 2 main types of joins that you need to know. One is nested loop join, one is block nested loop join. Okay.
So any join is a theta join.
Yeah, you can call it a theta join because theta is just giving you the condition for the join. This is just a representation.
No, any join.
Yeah, any join. You can write it in the form of this. Like if I want to do a left outer join, then my condition will change for the join, right? I will take all the common ones plus in left outer join, what do we do? Anyone?
Left outer join.
We take all the records in the left.
So we will take all the common tuples, right? Wherever we find a match, as well as everything that is left in the left side relation.
Yes.
So that is the condition for left outer join. So if we want to write it in forms of theta, then theta will represent this condition only. Okay. Okay, this is that same numerical that we solved. Now I'll tell you what is nested loop join. Okay. So let's say this is the hard disk drive and this is your main memory buffer. Okay. So in nested loop join, what happens? See. These are each of the blocks. Okay. These are each of the hard disk blocks that I have to transfer to the main memory buffer whenever I'm performing the join. So usually how is, if you tell me if I perform a join here, so I am matching on the ID attribute, right? So I will check this record with this. If I find a match with this, all of them I have to go and find if there is a match, right? So to find this match or to do this comparison, I have to first bring it into main memory. So in nested loop join, what happens? I first bring this block into main memory. Okay. If I take this block into main memory, then it will come here. Okay, can anyone tell me why I'm taking block by block? Why can't I take the entire relation into main memory? That will be easier.
It will be
memory has so much space.
Right, because main memory doesn't have that much space. Okay. So I can take, let's say, only one block at a time. So this Raj 101, Ram 102, and Rakesh 103. So this comes into the main memory first. Then I also take this block to the main memory. Remember, within each block, data is contiguous. Okay. So 101, 104, C01, C03. Now I can check. For Raj, I will first check. So in nested loop join, first Raj will compare with this one and this one. So it will find a match here, right? This 101 is matching. Then it has exhausted all its comparisons with this block, right? Only two comparisons. Next, it will again remove this block from main memory. Okay. Once that comparison is done, it will remove this block. It will bring
one doubt. If it is known that ID is the primary key, and once the match is found, why it will further compare and search for it?
No, this is just in general. Okay, I don't know if this is searching or not. In general. See, next it will bring this block. Okay, so now it is 106, 106, C02, C04. Again, Raj will check with 102. I'm sorry, 106, 106. Okay, it has compared with this block also. Once this is done, it will take the next block. Okay. So this is your outer relation. And this is your inner relation. Okay. So nested loop join, what happens? Every tuple of the outer relation or every record of the outer relation will first compare itself with all the records of the inner relation. Only then the next record of outer relation will start its comparison. So for every record here, can I say that I have, if there are, let's say, BR number of blocks in inner relation. Okay. So for every record in outer relation, how many block transfers do I have to make?
3, right?
I'm saying that, let's say inner relation has BR number of blocks. Here you can only see 3.
The number of inner blocks, ma'am.
BR, ma'am.
Number of inner blocks.
So all the number of, whatever is the number of blocks in inner relation, that will be the number of block transfer for each tuple here, right? So if there are n such records, then how many will be total number of block transfers? N into BR, correct? So nested loop join works like this. So now let's write the formula. So this thing, one more thing, this thing that I did, that only one block of data at a time can stay in the main memory. This is actually called worst case memory availability. Okay, worst case memory availability means I have the least amount of space in my main memory buffer. So only one block of data can go there at a time. What is best case then? Best case will be when I can take the entire outer and inner relations at the same time in the buffer, right? So in that case, there will be only 2 block transfers for the 2 relations. Understand? But we are going to work with the worst case anyway. Okay. I'm going to erase
This one is not the inner join.
Sorry?
No, this is not inner join.
No, this is actually not any type of special join. I'm just showing that any join that you want to perform, like inner join, natural join, if you perform it using nested loop join algorithm, okay, like this algorithm, nested loop join, if you use to perform that join, then this is what will be the cost. Okay, I will give you the cost now. Any join you can perform using nested loop join. Understood? Nested loop join is this algorithm that only one block at a time is going, and how the comparison is happening for every tuple of outer relation, it is going to first compare with all the records of inner relation. Only then the next tuple will start comparing. Okay. So if NR represents number of records in outer relation. Okay. BR, let's say, I'm just erasing this. So BR represents number of blocks in outer relation. NS represents number of records in inner relation, and BS represents number of blocks in inner relation. This is inner relation, this is outer relation. So what is the number of block transfers? Total number of block transfers is what?
NS into BR.
Now that I said that for every tuple or every record in the outer relation, you are having to bring all the blocks from inner relation, right? But you also have to bring these blocks. So there is a cost for that too. Outer relation block you also have to bring in the main memory. So that cost also you have to calculate. Okay. So I said number of records in outer relation is what? NR. And what is the number of blocks of inner relation? BS. Right? So first component is NR into BS. But again, this is how many times I am bringing the inner relation blocks into main memory. But outer relation blocks are also being brought into main memory. Na? So how many outer relation blocks are there? BR. So I have to do a plus BR. This is the total number of block transfers. Is this formula clear, or do I need to explain again?
Clear.
Clearly.
Okay, I'll still tell one more time. See, BR is number of blocks of this relation. Okay, let's say there are, in this example, how many? 3 are there. Okay, so 3 is NR, BR, number of blocks of outer relation. And what is the total number of records? What is NR? Just look at the data, 9. Right, 9 records are here. What is NS? Number of records in inner relation. How many are there?
6.
6. And what is BS? Number of blocks?
3.
3. Now, For first block, I have to bring this block from outer relation into main memory. This is one block transfer here, right? And for this block, for the first record, this Raj 101, okay, how many block transfers will be there from inner relation for the first record?
3.
3. For the second record also 3. For the third record also 3. So for one outer relation block, how many inner relation block transfers are happening? 3 plus 3 plus 3, that is 9. Correct. Now next outer relation block comes here. That is also one block transfer.
Ma'am, for one outer block, we have to take all the inner blocks in the main memory.
Yeah.
Then
See.
again, same for the second block in the outer block.
For every outer block, okay, I have 3 records in each block, right? And for each of these records, I have to bring each block of inner relation into the memory. Because how is it proceeding? For Raj, it will again first compare with this block, then compare with this block, then compare with this block. Okay. Next, for when I again search for Ram, now when I want to compare with Ram's record, then I again have to bring this block into the memory, the first block from inner relation. Okay, because the read-write head has changed. Right. So for every record of outer relation, how many block transfers of inner relation? 3. So for every block of outer relation which has 3 such records, how many inner relation block transfers will be there? 9. 3 plus 3 plus 3. Correct.
Yes.
But how many outer relation block transfers are happening? As many as there are blocks in the outer relation. That is 3. Right. So that is represented by BR. So NR into BS plus BR. Is this clear? This NR into BS is the total number of block transfers in inner relation. And this BR is number of block transfers in outer relation. So this is the total number of block transfer for nested loop join. Is this clear now? Okay. What is the other component of measuring query cost? This is block transfer. What is the other thing? Number of seeks. Number of seeks required. Now you tell me, what is the number of seeks required? See, this inner relation, okay. When you are trying to access the blocks of this relation, you have to access the first block, that is this one. Okay, only for this one, you have to do a seek, because after this, everything is in continuous order. Sorry?
For every block, there will be seek.
No. See. I'm saying that once you reach the first block, okay, then within that block, do you need to do another seek between 101 and 104?
Yes.
You will again perform a seek when you reach the when you want to go to the next block, right? Is that clear?
Yes, ma'am.
I think my internet is still having some issue.
So is it NR into NS?
Just a second, let me reconnect my net. Yeah. Am I audible now?
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Okay. So number of seeks required will be NR plus BR. What is NR? NR is number of records in outer relation. And what is BR? Number of blocks in outer relation. So BR number of blocks are there, right? So that many times for each block that I'm bringing from outer relation into main memory, I will have how many 6 for each block? 1 6. So BR number of 6, right? Then again for each block I have to bring this from inner relation into the main memory. So that will take NR number of 6. Why that? Can anyone explain why NR number of 6? Because for every block of this, okay, for every block of this, I have to start here in the first, correct? Let's say for Raj 101, once I brought this block into the main memory, for Raj 101, I will start the comparison, yes or no? So if I want to start this comparison, I have to bring this block into the memory as well, first block. So one seek will be here. Okay. Now after you bring this block, it will continuously check for these two records in the block. But then it has exhausted this block, it has to check in the next block. So that will take one more seek. Here also one more seek it will take. I have to change the read write head position. Right? Then again when you exhausted this block, you have to come to this block. So it will take one more seek here. So for every seek here, this entire block, okay, how many seeks in the inner relation? 3.
Yes.
Then I have to take the second block from outer relation. That is one more seek here. For that also same process will repeat. So for this one seek also there will be 3 seeks here, here and here. Now you tell me what is here, what is BR? Number of blocks in outer relation is 3. So for these 3 seeks, this BR component. Okay. And NR is what? Number of records in outer relation, that is 9. So see, that many times only we are having to perform a seek operation in the inner relation. For every outer relation block, there are 3 seek operations in inner relation in this example, correct? So 3 plus 3 plus 3 is 9. For that, this NR. So NR plus BR is the total number of seeks required.
It should be NR multiplied by BR, right?
No, it will be NR plus BR. Why? Because the seeks are different. No? For this relation, there are 6, and for this relation, there are 6. We have to add the total number of 6. See, if you want to write it in the form of multiplication, you can write it like this. So for one seek here, there are 3 seeks in the inner relation, right? For this block 1, for this block, for this block. So 1 into 3 plus 1 into 3 plus 1 into 3. Understood? For these 3 blocks.
Yes.
That's how we are getting 9. So NR plus BR. This is the total number of block transfers. This is the total number of seeks required. So this formula is important for numericals. Okay.
Ma'am, let's say there were 4 blocks in the outer block.
Then BR will be what?
12.
4. If there were 4 blocks in the outer relation, that's what you're saying, right?
Yes, ma'am.
Then BR will be 4. Right.
So in that case, the number of 6 will be 12.
It will again increase. So then 4 here. And for every such block, again 3. So that means how many? 1 into 3, 1 into 3, 1 into 3, 1 into 3. So 12. So total 16 6 will be there then.
So if we multiply, then we will get the result. I mean, the logic is the same. I mean, 1 into 3. But if we do multiply.
Yeah, for this part you can multiply this NR part. Okay, but you make sure to add this BR also.
Yeah.
For first, from the outer relation, we'll bring the first block, and for each record, we'll do 3 seeks.
Yes, because there are 3 different blocks here, na? And you have to check all the blocks of inner relation. For
So
every
for
record.
each outer block, there will be 9 seeks.
No. For each outer block, there will be 3 seeks because inside each block, there is no seek, na? Only for one block, one seek in the inner relation. Why you are saying it will be for each inner block, there will be 9?
Because for in each inner outer block, there are 3 records, and for each record, there will be 3 seeks.
So for each block, like for this entire block, that you are saying?
For each record, we have to get the 3 blocks or 3 seeks.
Yeah. So for each record, you will do this seek, this seek, this seek. Then again for Ram, you have to do. Again for Rakesh, you have to do. Okay.
Yes,
So
ma'am. 3 plus 3 plus 3.
That is why we got 9, no?
But I'm saying 9 for each outer block.
No, it will be NR plus BR. So BR is for every block here. Now for every block here also, what is NR? 9. Right? It won't be NR into BR. It will be NR plus BR. I think this is not clear for everyone. Okay. Wait, let me take another example. Okay. Let me explain one more time. This one was what? NR into BS plus BR. This is clear, right? Just the seek time.
Yes, ma'am.
Number of seeks required. Okay, let's do it again. So this is clear that I have to do one seek here, and one seek here. Okay.
Yes, ma'am.
Now for every record in this relation, we have to go through all the blocks of inner relation. Okay. Oh, I see. There was one mix up. Okay, sure. See, when we take the first block here, so I performed one seek for this block and took it to main memory. Okay. Now I have to perform one more seek to bring this block into main memory. Correct?
Yes.
This much is okay. Now, I think this is where the mix-up happened, that after I bring this block into main memory, okay, and I have compared, then I can directly go to this block because these are stored continuously.
Yes, ma'am.
Okay. So there is no more seek required for this block or this block. Again, when you go for Ram's record, then you need one more seek to come back to the first block. Okay, because disk can only rotate in one direction. So once you have gone in this direction, you cannot backtrack. So you again have to move the read-write head position to the first block, that is this one. So one more seek. So for every block of outer relation, there will be 3 seeks. Okay, 3 seeks for this, 3 seeks for this, 3 seeks for this. So 3 plus 3 plus 3 is 9.
But ma'am, Ram is under the Raj or in the same block.
Yeah. Inside the same block, there are no seeks required. Okay. So you might ask that if I don't need seek for this block and then this block, from one seek only I can go, then why do we need seek for this, right? Because once I come to this block and I bring it to the main memory, then I am positioning the read-write head according to this inner relation, na?
Yes.
So when I go to the outer relation to change the block, then I again have to perform a seek because the read-write head has now changed position. So that's why every time I access a block from outer relation, I need to perform a seek. But every time I want to traverse through the inner relation, one seek is enough to traverse through all three blocks. Okay. So for every outer relation block, there will be 3 seeks, one for each record. Okay. So now the formula will be NR plus BR. Now this makes sense, right? BR is 3 and NR is 9. So total 12 seeks. Clear now? Any question?
Ma'am, we can also write it as BR into BS.
BR into BS. Actually, I don't think you can write that. See, blocks of outer relation and blocks of inner relation will not be always same in number, na? Why are you saying BR into BS? What is the thought process?
No, for each block in the outer, we have to do. Okay, okay, ma'am. No.
No. BR into BS will give a different thing. I got what you thought. No. It will be NR plus BR only. This BR is the component for outer relation 6 and this NR is just representing inner relationship 6. That is how many times you have to seek in the inner relation.
Ma'am, it is like BR for the number of block in the outer relation into 1. That 1 is the seek which I do on the inner block.
Yeah.
Plus NR into 1.
So this NR is just representing the number of seeks in inner relation.
Inner relation.
Yeah. So let's do a quick numerical on this. Take this one. So consider the information given on project and allotment. Okay. This is the number of records and number of blocks given for two relations. Now considering worst case memory availability, that is only one block can go into the main memory buffer at a time. So assuming allotment as outer relation and identify correct cost estimate for nested loop join of these two, where allotment is your outer relation. So you give me the cost, how many block transfers and how many seeks. So first let's calculate number of block transfers. What is the formula, anyone? Okay, first you tell me, what is NR here? NR is number of records in outer relation. Allotment is outer relation.
9,000.
So 9,000 is the number of records. What is BR? Number of blocks of outer relation. What is that?
600.
600. What is NS? Number of blocks of inner relation. Records of inner relation. 2,000. And BS is number of blocks of inner relation, that is 200. Okay. So what was my total number of block transfers for nested loop join? What is the formula? NR into BS plus BR. So perform this. What is NR? 9,000 into BS is 200 plus BR is 600. So how many is happening here? This. So that is 18,600,000. This many block transfers. This is okay? Is this clear to everyone? Just formula I put. Okay.
Ma'am, how do you get this NR, NS, BR, BS?
See, it is given in the chart, na? See, allotment is outer relation. That is mentioned in your question. Okay. What is NR? NR is supposed to represent number of records in outer relation. So check here, number of records of allotment is 9,000. Okay. BR is number of blocks of outer relation, that is 600. Similarly for inner relation you can find. Okay. So this is one of the metrics of cost measure. What is the other metric? What is the other one along with block transfer?
Seek time.
Number of seeks. So what is the number of seeks in nested loop join? We just saw. What is the formula?
NR plus BR.
NR plus BR. So what is that here? 9,600. So this option is correct. This is the type of numerical you will get from here. Okay. Is this one clear to everybody? Any question?
Yes, so it is like NR into 1 plus BR.
Yeah. Just you can remember like this only, NR plus BR. Easy way to remember. See, you have already a lot of things to remember in DBMS. Okay. That's why I don't want you to like get jumbled up during the exam time. So just remember a few formula that I'm giving. Okay. Yeah, definitely you need to understand how these formulas are coming, but just try to remember them as they are. Okay. So can I go to the next question?
Yes, ma'am.
See, this one. Similar question, it is saying, consider worst case memory availability, assignment as outer relation. Again, perform nested loop join and tell me the correct cost estimate. This one you will do. I will give the formula. Number of block transfers is NR into BS plus BR and seek is NR plus BR. Solve it and tell me the answer.
B option.
Which option?
B.
B. You're saying this one. Any other answers or this is the one?
B.
B. Okay. Let me solve once quickly. So NR into BS plus BR is 5,000 into 100 plus 300. So this is giving 5 lakhs 300. This is number of block transfers and number of seeks is NR plus BR, that is 5,300. So option B is correct. Okay. Next is, so these two okay for everyone, right? From nested loop join, this is the type of question you'll get. Next one we will do is block nested loop join. Okay.
I mean, nested loop join, only these two formulas are enough.
Yeah, only these two formula is enough. This one is now block nested loop join. Okay. So the only difference in execution is what now? This is again main memory buffer and this is your hard disk drive. Okay. So here what happens? First you will take again this block to the main memory. Okay. So this is Raj 101, Ram 102, Rakesh 103. Here you have 101, 104, C01 and C03. So what happens here? Here you will first do this. Raj will compare with this. Raj will compare with this. Okay. Then instead of taking a new block, Ram will also compare with this. Okay. And this one. Hello, am I audible?
Yes, ma'am.
Sorry, how far did you listen? This block nested loop join, I just started, right?
Yes, ma'am.
Lost my connection, I'm sorry. Okay. So I was saying that here, first Raj will check with both the records of this one. Okay. Then Ram will check with both the records. Then Rakesh will check with both the records. Okay. Once this is done, then I will change the block. This one, I will delete this. Okay. And in place of it, I will now bring the next block here. So this one will now be 106, 106, C02, C04. Okay. Similarly, Raj again will check with both these. Okay. Ram also with both. Rakesh also with both. Okay. Then once this is done, again I will go fetch the next block. Then once this whole thing is done, then I will go to the next block in the outer relation and again repeat the entire process. Okay. So what will be the total number of block transfers here? Any idea? What will be the number of block transfers?
3, right?
No, for one outer block, 3.
I'm asking in general. Like, you don't have to give me a number. Just give me a formula. Using those same 4 variables, NR, BR, NSBS. R is for, NR means number of records of outer relation. BR is number of block.
In this case, NR is 3 into 3.
So BR into BS.
So you're saying BR into BS. Anything else you're missing? This is for inner relation, right?
Plus BR.
Plus BR. Correct. This is the formula. See, you only can derive. No need to even remember. So how did we get BR into BS? Because for every inner relation block, for every outer relation block, how many seeks do I need in inner relation?
3.
How 3?
No, 1. 3 block transfer.
Only 1, right? Because for Raj, I will first go here. Okay. And then I can keep this one and then do the comparison with Ram and Rakesh as well. Right. Then I will again go to the first block. Then I will remove this block entirely and I will bring the next block. Then again check with all 3 here. Then again remove this and bring the next block. So how many seeks do I need for, can anyone tell me how many seeks per outer relation block?
BR.
BR or BS?
BR.
Explain. How you are getting this BR into BS, explain.
For one outer block, you have to do like 3 inner block transfers.
For every outer block, we should fetch every inner block.
Right.
That way it is clear.
Exactly. So it will be, in this case, it will be 3 into 3, right? Plus 3 for this outer block transfers. So this is the number of block transfers in block nested loop join. What is the number of seeks? Number of seeks will be 2BR. How 2BR? See, for every block here, I only have to do 1 seek here. Right. So first I do 1 seek to get this block from hard disk to main memory. This is fine.
In the inner block, are those blocks serially arranged?
See, inside a block, the records are serially arranged.
Yeah, outer block it is apparent, but in the inner block,
inner relation also. Inner relation also, the inside this, the records are serially arranged. Okay. And the blocks are also serial.
Okay. But the blocks are differently drawn, that's why.
And that's why this is happening. See, first I took 1 seek to get this outer relation block into main memory. Okay. Then I have to do one seek to get here, inner relation block into main memory, correct? This much is correct?
Right.
After that, I can just go serially to this block and this block, no more seeks required.
But the blocks are different, no, ma'am.
Blocks are different, but see, my read-write head is where? After I transferred this to main memory. Okay. Then once I perform this seek and reach this block, okay, then I can just contiguously go and locate this block and this block also. Now they are all continuously stored on one track.
So, ma'am, in the exam, how would you know the inner blocks are serially
No,
transferred?
this is a given. All of these blocks are sequentially stored. Even these outer relation blocks are sequential. Why I need different seeks for each block here is because I am changing the read-write head to this position. Okay.
But for the worst case, we have to fetch every inner block at a time.
Yeah.
In that case, the seek will be more, no?
No, seek will remain same. See, worst case is what? That I have to do all the comparisons. Right, for all three blocks here, outer relation, I have to compare with all three blocks here.
Yeah.
Right. So first one seek to bring this first block into main memory. Then again one seek to get to the first record of the first block in the inner relation. But once I do this seek, then I can just serially move on to this block as well as this block.
Okay, and it will be given in the question.
Yeah, you can just take this in general. Okay. Even if it's not given in the question, this is the pattern you'll follow. Okay. Then when I want to take the next block from outer relation, then I have to change the read-write head position to this. So one more seek is here. Again one seek to get to the first block of inner relation. Again one seek for this block and one seek here. So total, how many seeks are there? For every seek and for every seek for every block in the outer relation, there is one seek in inner relation. So if there are BR number of blocks in outer relation, it should be BR plus BR, that is 2BR. Is this clear? How we got 2BR?
Yes, ma'am.
Anyone wants me to repeat this?
Yeah, ma'am. Please repeat why you're getting. Ma'am, first I got 1 BR. I into the number of the seek on the inner join.
Okay, let me write in that way then. See, one seek here, right? To get
Yes,
outer relation here.
Yes.
Then one seek here to get this first block of inner relation into the main memory. Correct?
Yes. Yes.
After that, what am I doing? I am matching all the records of this with this.
Correct.
And then I'm changing the block to this block.
That
So
is
when
anyway
I'm changing
sequential,
it
no,
here-
ma'am. So no need seek there.
Exactly. So no need for seek. So I can directly go here, then I can directly go here also.
Yes.
So I have done all the comparisons for first outer block.
Correct.
With how many seeks? 2 seeks. One here, one here.
Oh, okay. I got it, ma'am. Okay.
Okay. Then the next seek will be for this outer and again one seek here.
Yes.
Like this 2 plus 2 plus 2.
Got it.
6. Okay. So BR plus BR. 2 BR. Clear? Now let's do some numericals on this. So this is the numerical. NR first, write the NR NS values. Okay. So you don't forget that. So it is saying allotment is outer relation. What is NR? 9,000. What is BR? 600. What is NS? 2,000. And what is NR? 200. So give me what is the total number of block transfers? You yourself told the formula. What is it?
BR into BS
Plus
B.
BR. So what is this giving? Calculate 600 into, sorry, this one I wrote wrong. This is BS, okay. So 600 into 2000, I'm sorry, 600 into 200 plus 600. This is how much? 1,20,600 block transfers. How many 6?
2 BR.
2 BR. So what is BR here? 600. So 2 into 600 is 1206. So option D. Correct. Do this one. Tell me the answer. Quickly do this.
Option D.
Option D. This one you're saying?
Yes, ma'am.
Anyone else got a different answer or everyone is agreeing?
Yes, D.
Okay, let me quickly do it once. So BR is what? Tell me what is BR? 300
300
into what is BS? 100 plus BR. So this is 30,300. And what is 2BR? 600. Okay, option D. Okay, so this is all the important things from week 12. Okay, now week 12.2, you can just go through the lectures. It's mainly about, I think, some relational algebra expressions are there. Okay, I won't say memorize anything. Okay, just go through the lectures, and the last 3 are mainly theoretical. If you want to read those, you can, but mainly whatever I covered in these slides, this is the important part for week 12. Okay, if you want, I can post these slides on Discourse. Okay.
So in 12.2, there are some equivalence relations, conditions.
Yes, yes. Some theory part is there. Also, some trees are there for relational algebra. You'll see in the beginning. Okay. So those things you can just go through the lectures once and the slides. If you don't understand anything, you can ask us on Discourse. But for our exam point of view, this is all that is important. So should I post this on Discourse or is it fine?
Please post it, ma'am.
Okay, then I'll give you these slides. Now for n term, the weightage, okay, from weeks 1 to 8 will be 40 to 50%. Okay, and 9 to 12 will be 50 to 60%. So you study accordingly. Now, week 11, any doubts? Tell me, what are the doubts?
Before that, in 12.2, there are some equivalence rules. So in the exam, whether we'll be asked some relational algebra and then we'll be asked to convert it.
From SQL to relational algebra, you're asking?
No, ma'am, how to go from find out different equivalence relation. It's a relational algebra for.
Just do the tree notation. Okay, that part you can just look over once. Wait, let me open 12.2.
Ma'am, please schedule a session in the next week for revision session of week 9 to 12.
Yeah, next week we'll have revision sessions only.
Okay. Please do as soon as possible.
Thursday there will be a revision session from week 1 to 8. Okay. And on Saturday I will take from week 9 to 12.
Ma'am, in that week 1 to 8, 2 and 3 and 7 we can ignore, ma'am.
No. You have to go through all the weeks. Okay. So 7, that Python DB connectivity part is not that important for theory exam.
Okay.
But weeks 2 and 3 are very important.
Okay, ma'am. No, because we wrote so many SQL, no, ma'am. That's why I asked. Okay.
Yeah, no, but we'll take up everything in revision session.
Okay, sure.
Here, 12.2, I'm talking about this part. This. Just this much is enough. Okay, this query equivalence thing. Just these trees. Okay. No need to go into all this theory. No need to remember all this theory part. Just this trees and maybe this equivalence relation you can go through once. Okay. Any of these equivalence rules, if it's not clear to you, you can just post it on Discourse. I'll give you a PDF on this. Okay. But no need to go to too much depth in this. Just the PDF that I will share, if you, this one that I just took the class in, that one is So week 11, which topic was not covered? Anything you want me to cover?
Just one doubt. Like in week 12.2, like from one relational algebra expressions, professor is using the equivalence rules and converting it into another type of.
Yeah. See, that thing you can go through once. That is actually okay. You can go through it once. See, in PYQ you will find 1 or 2 questions from that. Okay, so just try to solve those questions. That is enough. Okay.
Okay.
In PYQ, I think 2 questions are there from that part. But mainly this block nested loop join and nested loop join is very important for week 12. Okay. Yeah, week 11, any topic? Okay. So if you do have any issue with that RAID architecture part or anything, you can ask me on Discourse or anyone, me or you, sir, you can ask.
Ma'am, there was one graded assignment question, ma'am. Question 8 of week 11, I think. Will that kind of question come?
Okay, let me check. I don't know what is that.
That RAID and parity, ma'am. Because
was it some formula-based question?
It was not formula, ma'am. That parity will be there 1 0 0 1 1 1 1. Okay. That XOR loop, I mean that algorithm. I didn't know that algorithm and all, ma'am.
Okay, just let me check the graded assignment. Which one?
Week 11, question 8, I think.
Okay. So this question.
Yes, ma'am.
Okay. See, this type of question I have discussed in last term's week 11 lecture. Okay. I have discussed exactly this type of question. So you just check that lecture once. Okay. If you don't understand, then you let me know. I will explain it to you.
Okay, ma'am. I will look into it.
Even in end term, I think in end term revision also this type of question is taken. Other than that, in week 11 also I have taken it last term.
Okay, last term week 11 open session, is it, ma'am?
Yes. The one that I took, that one. Okay. I think 2 sessions are there. Just
I will check and I will look at it, ma'am. No problem. Thank you.
Okay. Actually, this is actually important. Okay, RAID architecture is important. But in RAID architecture, you will see that there is a chart, right? Given at the end, you will see different RAID architectures and all their properties.
Yes.
I would say go through that chart. That is much easier to remember. But if you go through my last term's session where I took it, I actually underlined all the parts that were important in RAID architecture. So you just study those. Okay.
Okay.
I will remember all the theory.
Okay.
Okay. So
can I ask one doubt?
Sorry, can't hear you.
Can I ask a doubt?
Yeah, sure.
I need to share my screen.
Okay. Wait, I'll stop sharing.
Yes.
Yeah, go on.
The one written in blue, we assume that if a transaction.
We
I'm
assume
doubtful
that
that.
if a transaction Ti has modified an item, no other transaction can modify that same item until Ti has committed or aborted. Okay. Yeah. So why is this written? This is actually that thing. Remember that if some data element is updated by transaction Ti and transaction Tj wants to read that and perform something on it, okay, then Ti's commit has to come before Tj's commit if we want it to be recoverable, right?
Yes, ma'am. I'll show another slide, week 10.
Ma'am, this is a transaction lock. I think it is talking about. So am I right? Like if
This is the recovery part, no? Like that cascadeless schedules. These things are in recovery part. I don't think this is locking.
No, but here this is from week 10. Like I took some example.
Is this slide from that locking part? Okay, that previous slide that you showed, was that from locks?
No, week 11.3 backup and recovery.
Okay. Backup and recovery. Yeah, that's what I'm saying.
And
Okay,
this is from week 10. This slide.
Okay, cascade-less schedules for each pair of transactions Ti and Tj, such that Tj reads a data item previously written by Ti.
No,
Yeah.
this example, like in 11.3, it was written that until a transaction commits or aborts, another transaction cannot update the data item, right?
Yeah.
But here this T10 is writing A, and then before T10 is aborting or committing, T11
Because see, why this is working, why this is still recoverable is because the abort of T10 is coming first. Okay. See, T11 and T12 haven't committed yet, right? No one has committed. But after this happens, this abort operation in T10 comes first, na? So what will happen here? If this abort executes, then what will happen?
Then it will be cascading.
But this is a cascade-less schedule. What is a cascading schedule? You tell.
Ma'am, it is a cascading.
See, for each pair of transactions Ti and Tj such that Tj reads a data item previously written on by Ti, commit operation of Ti appears before the read operation of Tj. Okay. Every cascade-less schedule is also recoverable. Cascade-less. So this schedule is, yeah, exactly. This is cascade-less, not cascade-less. This is a cascading schedule. If this abort operation happens, then all of these transactions have to be rolled back. Okay. All T10, T11, T12, all of them have to be rolled back.
Yes, ma'am. But it was written that until a transaction commits or aborts, another transaction cannot update. Right? But here
that is when it is recoverable.
Well, this is also recoverable.
This is not cascadeless. Now, every cascadeless schedule is recoverable, but this schedule is not cascadeless.
It is cascading recoverable.
Is this recoverable?
Yes, ma'am, because T11 is not committed.
Because no one has committed, right?
Yes, ma'am.
So this, you can recover this schedule. Okay, but it is not cascadeless. That thing that is written there in the previous slide that you showed,
yes,
that if a transaction Ti has modified an item, no other transaction can modify until Ti has committed or aborted. Okay, this is the condition for if you have a cascading schedule. Okay, like other transactions, like more than one transaction in a schedule, and other transactions are depending on a previous transaction's data. Okay, like in data item A, if T10 committed a write operation on A, then T11 read that same data variable A. Okay. Then it is mandatory that T10 has to commit before T11 commits. Okay, then we can definitely say that it is recoverable. That is what it is saying.
So this is for cascadeless recoverability.
This thing is for to ensure that a schedule is recoverable. Cascading cascadeless comes later. This is the basic condition for recoverable schedule. That if there is a write-read conflict on the same data item, okay, you can think of it like that, that someone is writing and then I am trying to read that same data item. Then that transaction which wrote first, that has to commit or that has to abort before my transaction which is reading the data item can commit. Okay.
Yes, ma'am, but here before T10 is committing, T11 is reading, right?
Yeah, it is
So that
reading.
is not
But
matching.
T11 has also not committed. No. None of these changes are permanent. If T11 committed and then this abort happened, then it would not be recoverable anymore.
What is his doubt actually? Read will always be allowed, no? Whatever transaction is happening, it
Yeah,
will not
read is
block.
always allowed. Yes. Just you have to make sure that where you are reading from, that is that last transaction that made the write on that data item, that should commit first if you want to ensure recoverability.
Yes, ma'am, but it is written that no other, before it commits, no other transaction can also even modify. Like it is not committing.
Read is not modify, right? Read is just a read.
Yeah, but there is also write
Right.
operation, I think he's saying.
Yes,
Okay.
ma'am.
But that write operation is also not permanent since it is not been committed. Okay, so as long as the commit of that previous transaction comes before, then it is fine.
So this is like when one transaction is modifying an item, no other transaction can commit that change.
No, you cannot commit that change before that transaction does.
So this modify, this word can be taken as commit, right?
Yeah, you can think of it like commit because until and unless you commit a change, it is not permanently changed in the DB.
It's kind of version controlling implemented, right? Like if we multiple developer working on the same code base, how they manage the code, it is something similar concept here also, I think.
Exactly, because if a transaction, let's say that T10 example, if that T10 transaction, it let's say made some changes to this variable A, and then that changed value of variable A is being read by transaction 11. Okay, but transaction 11 committed the changes that it made to variable A before transaction 10 did. Now, if there is a failure before transaction 10 can commit, then the whole thing becomes wrong, inconsistent. Right, because the previous data that was modified by T10 was never committed. Although another different transaction T11 has already committed that data somewhere else by reading it. Okay.
Okay, so that is what is written in this two lines.
Yeah, this is recovery. Actually, this is the main condition for recovery.
Yes, ma'am. Okay. Thank you.
See, in week 11 also, I'll ask you just check out the lecture from last term, okay, if you have any doubts. Because there I had actually told all the important topics and everything, and I discussed a lot of numericals. So you just check that out once, okay? Okay, that's it. I don't have anything more to tell in week 12. So next session will be revision session from weeks 1 to 8 on Thursday. Okay.
Thank you, ma'am.
Thanks a lot, everyone. I will post this week 12 PDF on Discourse, okay?
Thank you.
Thank you.